This is CPE 133. This is from the Free Range Verilog Foundation Modeling, Chapter 15. And what we want to talk about here is shift registers. Well, here's the disclaimer. The only way to learn Verilog is actually grind out some circuits. You're not going to learn it by reading about it or watching strange videos about it. Just get out there, do it, generate some problems, get your problems fixed, ask a lot of questions. So shift register is another type of registers. We first started working with just basic registers. I call them simple registers. We then moved on to counters, and here we are at shift registers. Shift registers retain all the features that you'd expect of a register, such as loading and clearing, but now with the shift register it also shifts. And so we have the issue of shifting left and shifting right, which is very useful in digital design land because the shift left is a multiply by 2, a shift right is a divide by 2. Typically all the operations in a shift register are synchronized to the clock edge, and thus it's a synchronous sequential device. And so this is our typical block diagram for what I call a universal shift register. So shift registers are not super useful if it only does one thing, like shift left. Typically you have shift registers or modules that do all sorts of stuff, and namely shift left, shift right, maybe a rotate, etc., all sorts of different things. But the issue is it is loadable. So this is the input data that becomes the output data when it's loaded. You can clear it, and the last thing here is typically it's universal shift register, so it does a whole bunch of operations. This is the select input, which is going to select which operation the universal shift register is going to do. Now the other issue is a D bit. I thought I'd draw a picture up here, and the issue is here's just some register, and what I'm going to do with this thing is shift it right. And so once I shift it right, these right bits go down here, so this is lost. These come over like this, and this becomes the D bit. So it loses this bit and it has to add a new bit, but the bit it adds is configurable, which I call the D bit. Some shift register is just not configurable, but heck, you can design it any way you want. We're going to go through an example here, and this is a universal shift register. What I need to do is just declare what's synchronous and what's not. So the thing that's asynchronous is the clear input, which we've seen before. And these are the operations that I'm going to do on it. So I'm going to be able to hold, I'll be able to load, shift left and shift right. Without saying anything about this, these are just simple shifts, so shifts of 1 bit position. So let's crank out the solution real fast. And it's, once again, it's nothing real new in this. It is a parameterized model, so here's the parameter. Thus it defaults to an 8-bit shift register if you don't override that parameter when you instantiate it. This is the memory portion of it. It is sensitive to both the clear signal and the clock signal. The clear signal is an active high asynchronous reset. So as you would expect, the procedural programming statement, or the if statement within the always block, checks the clear first. Typically clear is going to have a higher priority over the other operations. Now if this fails, if it succeeds, it clears. Okay, if it fails, it is going to go into this else statement down here, and the else statement does the interesting stuff. So we're looking at the hold operation. Here's the hold operation, so the data out becomes data out, which is essentially saying the old data out becomes the new data out. I can actually load a new value into this thing. So what it's going to do is take these input bits here and load it into the shift register, so the data out becomes the data on the data in lines. Next we have a left shift operator, which is this option right here, and left shifting is essentially going to go something like this. On the left shift, I'm going to take the bits from this, I guess I don't need that, this original register value, shift it to the left. These are all shifted to the left blah blah blah. This one's lost, and this one becomes the new bit. Okay, so there it is. There are the bottom n-1 bits become the new top n-1 bits, and then the least significant bit becomes that D bit, and that's for a left shift. Now for the right shift, it's going to take this, it's going to do the same thing. We'll say it's going to lose this bit, and then the D bit is going to be placed on the other side. Okay, so here's the D bit, here's the bottom n-1 bits. Now essentially it goes from n-1, which is here, down to 1. That's the bits I want to go here. Notice I have used this concatenation operator. The concatenation operator reads left to right, and so the order that I place these bits in here is the order they are going to be placed in the actual data out value. This is a sequential circuit, so I do use non-blocking operators in there, non-blocking assignment operators. It uses this case statement. I've included a default in this, but I didn't need to because I actually specified every case in the 0, 1, 2, 3, every possible case for the 2-bit select signal. I like seeing defaults in there all the time, even though that should have a colon on it. It just makes more sense to me. I actually don't like to rely on the default to actually implementing the case. And so that's it. Another way to do this, which we'll get into next. This is another example problem. It's very similar to the last problem, which means we can use that code, of course, as a starting point. But the difference being is that this problem calls out to use the special operators for shifting. Now the shift operators are this for shift right and this for shift left. And those are operators as part of the Verilog system. Certainly we can use them in our design. Now the issue is that when I use these operators, now you're going to lose bits, but you're going to lose a bit or as many bits as you're shifting off, but you're also gaining bits. The difference being in this is that the bit you gain is automatically a 0 when you use these operators, whether you're shifting left or right. So that means that this used to have a D bit option. It is no longer in this model. So that's one of the changes you're going to see in this one. Other than that, we're just going to use the operators. So the D bit, it is parameterized. The D bit is missing. It's missing up here too. We don't need that anymore. Everything's exactly the same. It is an asynchronous reset. But only thing that's different is these two values right here. Instead of doing this manually, we use these shift left and shift right operators. Now the issue with the shift left and shift right operator is that it is a binary operator, which means it has two sides on it. So this is the thing you're going to shift. This is how much you're going to shift it by. Since these were basically simple shifts, I only need to shift it by 1. 1 is a constant value. Certainly I could shift it as much as I wanted, but like I said, these are simple shift registers. This also includes the default case as for the arguments we presented previously. And that is it in this thing. Once again, the difference between doing it manually and using these shift operators is you lose control over that bit that's going to be insert as a result of the shift operation. So there are other shift operators in Verilog. Essentially, there's arithmetic shift operators. Here's arithmetic shift left. This is arithmetic shift right. Now these are a little bit tricky to work with, essentially because you have to declare the numbers signed in order for them to work as you would expect. Or you can additionally, you don't need to declare it signed, but you need to cast them as signed. For a shift left operator, a shifting left in this direction, if it's a signed number and it's shifting left, the sign bit is retained. The sign bit is never lost. It's actually the bit to the right of the sign bit that is lost. For shift right operations, if it's a signed number, sign bit is propagated toward the right. Now this is so if the sign bit's 1, it gets filled with 1s. If it's 0, it gets filled with 0s. So essentially, it's sign extension in the other direction. The other type of operations you typically see out there are barrel shifts, which are essentially what we have in this slide here. Because we've only shifted once, that's a normal shift, but if these values were greater than 1, it would be considered a barrel shift. So these are quite easy to do. But then there's also the notion of rotates, and this is something that's not supported with Verilog operators, but it does make for a good problem in Verilog, which we'll certainly come across. So in summary, shift registers, type of registers, retain all the features of registers like loading, clearing, all that fancy stuff, but it does do other things such as shift left and shift right. So shift left, 1-bit position, is a classic multiply by 2. Shift right is a classic divide by 2. Now, once again, these shift operations very straightforward to model in Verilog using behavioral modeling, and typically we don't really just design a shift register. We design some type of universal shift register that does all sorts of fancy shifting in one module dependent upon a select input. So there's 2 types of operators in Verilog basically supporting shifting. There's just the regular shift operators, and then there's the arithmetic shift operators.